Alright, please let's share the link with our friends so that they can also join and then benefit from this section. So I'm going to continue from where we ended. So I was talking about Thevenin and then how to calculate for the Thevenin's voltage. So I'm going to redraw the equivalent circuit I drew down here. So as I was saying, the steps 1 and 2 in Thevenin says that we should take away the load resistor. That is the one in question. So in this case, it's the 2 ohm resistor. So I'm going to take it from there. Alright. Reciprocity and superposition. Yeah, we are going to consider that. Okay, so let's bring our 3 ohm resistor here. So we have our 7V here, our 5V here. Okay, so the third step says that, yeah, I'm going to go over. The third, alright, I'm going to go over. So as I was saying, in Thevenin, there are rules, there are steps we need to follow to be able to solve a question under Thevenin. Okay, so the very first thing you are supposed to do is take away the resistor in question. You see now the question is saying it is desired to use Thevenin's theorem to find the current in the 2 ohm resistor of the circuit below. So this 2 ohm resistor is the resistor in question. Okay, this resistor is our load resistor, the one we are talking about. So the first step says that we should take it from there and then we should name our terminals A and B. So I've taken it from there and then I've named my terminals. Yes. So that is the very first step. And after we are done, we are going to solve this. Okay, let's bring our VTH here. Like I said, don't forget, this is an open source, okay, open circuit, but it's considered as a voltage source. Thevenin's voltage is the open circuit voltage source. So you have to put the VTH across here. Always. Don't forget. Alright. So moving on. As I was saying, this 7V here is going to drive a current. Okay, voltage sources produce current. Oh yes, we can assign the VTH at the other direction too, but we are going to get the negative, direction. So we are going to get the opposite of the other one. Yes. So let's say the current, it's I1. The current that this 7V is driving is I1. Like I was saying, when it gets to this node, ideally it's supposed to split. Okay, but because of this open circuit here, current doesn't like stress, so it won't continue. It will come down. Okay, so it's the same I1 that will come and pass through this resistor, and when it gets here, it goes back to the node. So someone may ask, why is that when it gets here, it comes this direction, but then not this direction? Anytime current leaves a node, its main aim, okay, is to go through the circuit and return back to the source, passing through the least possible branches. Okay, so if it gets to this node here and it chooses to go this direction, you see it's going to the wrong node. Okay, so when it gets here, it won't continue here, it will come back to its source, that is the 7V here. Okay, all right, so as I was saying, we are going to solve this using KVL, and I explained KVL. KVL states that the summation of voltage sources in a loop is equal to the summation of the voltage drops. Okay, I explain what a voltage drop is, and also the voltage source we all know, the 5 and then the 7. So after I'm done, I'm now going to solve this using KVL. So I can choose to take this loop here, okay, or the bigger loop. The main aim is to make sure the loop you choose has VTH in it, so that at the end of the day, you are able to solve for VTH. Because just imagine you are trying to solve for A, but then your set of equations doesn't involve A. I mean, how do you get it? Do you understand? So you should make sure your loop involves VTH, so that at the end of the day, you're able to solve for VTH. So it's because of the short circuits. That's why the currents. Please, can you come again with your question? I'm not getting it well. All right. So yes, let's write the equation for this loop here. Okay, loop A. Now, because it's moving in this direction, see, current moves from the positive terminal of the voltage source. So this loop here, we are going in the same direction as this 5V. So it's going to be positive 5. Okay, when we get here, you can see we are going in the opposite direction of the VTH. So it's going to be minus the VTH. Okay, right now we are done with voltage sources. Let's consider voltage drops. So KVL says that we equate the summation of the voltage sources to the summation of the voltage drops. So this is equal to, now when we get here, we can see there's a drop here, right? And the drop here is, as I said earlier, the current times the resistance. So we are going to have I1 times the resistance there, that is 1. So this is going to be our first equation. 5 minus VTH, which is equal to I1. This is going to be our first equation. Also, we can consider this loop. Okay, we are trying to write two equations so that at the end of the day, we are able to find our VTH. Now, considering this loop, let's call it loop P. Now, we can see that it's in the same direction as the currents being driven by the 7V here. So this 7 here, once again, is going to be positive. We are writing the equation for KVL, this loop. Now, when it gets here, okay, there is just one voltage source. So 7 here is equal to, there's going to be a voltage drop here. Now, it's the same I1 that is passing through this 3 ohm resistor. So the voltage drop here is going to be what? I times R, which is, and then the I there is I1 times R, which is 3. Now, when it gets here, once again, because of the open circuit here, it's not going to continue. It's going to come back, okay? It's going to drop down here. So when it gets here, it will come here and then back. So there's going to be another voltage drop across this 1 ohm resistor. And what is it going to be? 1 times the resistor there, which is, sorry, I1 times the resistor, which is 1. Sorry about this. 7 is equal to 3I1 plus another I1. Okay, so we are going to have what? 7 to be equal to 4I1. Now what's our I1? I1 is going to be 7 on 4 amperes. Okay, I1 is going to be 7 on 4. Now, from equation 1, we can see that, let me write up here, we can see that our 5 minus VTH is equal to I1. Now, given that I1 is equal to 7 over 4 amperes, our VTH will be what? 5 minus 7 over 4. What are you going to get for VTH? 3.25 volts. That's our VTH. Now, number 4 is what is the value of the Thevenin's voltage? Our VTH is what? 3.25, which is this. I hope we all get it. Can I see yeses in the comment section, or a no? If you don't get it, I get to know if I should continue or not. Please, do we get it? Please, let's see in the comment section if you get it. So can I continue? Okay, all right, thank you. So the question 5 is asking us to find the Thevenin's resistance. Now, the Thevenin's resistance RTH is equal to the total or the effective resistance of the circuit. But one thing I need you to never forget is that the RTH is equal to the total resistance of the circuit when all sources, when I say sources, I mean both current sources and voltage sources, okay, have been deactivated. Do we get it? When all current sources and voltage sources have been deactivated, that is when we find our RTH. So now we are done with VTH. Let's find RTH. So let's go back. Now this is how the circuit looks like. This is the question. Okay, in finding RTH, once again, we are going to put our RTH inside where we removed our resistor. And then this is what you are going to do. How do we deactivate all sources? For voltage sources, this one is something you don't need to forget. For voltage sources, we short circuit them. Okay. But for current sources, we open circuits them. Okay, so let's draw it again. This is how it's going to look like. Once again, my points A, B, I'm going to have my RTH there. Okay, now there was a voltage source here. This 5 here, we are going to short circuit it. Now, short circuiting it means drawing a straight line through that path, or I mean having a short circuit across it. So it's going to take away this ohm here. So essentially, we are going to have nothing on this branch. Okay, when we get to this the 1 ohm inside there, we are still going to bring it because it's not affected. All right, now the next 3 ohm resistor here is also not affected. But guess what? When we get to this part, we are going to short circuit it. So it's going to take away this. So essentially, we are going to continue this way and then back. So this is how our circuit is going to look like. Okay, this is how our circuit is going to look like. Now, RTH is the total resistance. Okay, looking through the terminals. Now, the terminals are A and B. Now, looking through this terminal, what is the total or the equivalent resistance of this circuit here? Now, we have 3 here and then we have 1 ohm here. We can clearly see that once again, this here, the 3 ohm resistor here is connected in P with this one, in parallel with this one. Okay, somebody is saying he doesn't get it all. So I'm trying to say that in calculating the RTH, what we do is that we first of all short circuit all voltage sources and we open circuit all current sources. Now in this question, there are no current sources. In this question, there are no current sources. Okay, so we are not going to have any problem with that. But there are voltage sources. In finding RTH, what we do is that anytime we see a voltage source, we short circuit it. Now, short circuit is a branch that has no resistance. A branch that has no resistance. So, anytime you see a voltage source, you draw across that voltage source a branch that has no resistance. That is essentially what you are going to do here. Okay, so let's draw the circuit again. Let's draw the circuit again. Once again, I'm going to take away the 2 here, okay, because that is our load resistance, and we are saying we take it away and we put RTH there. Now, this 5 here, we are going to short circuit it. That means you are going to draw a branch that has no resistance across it. Now, if we should draw a branch across it, it's going to take away this voltage source from there. Okay, why? Because once again, short circuiting the voltage source means giving it a path that has no resistance. So we are going to short circuit this. So it's going to take away this 5V from here. And then this 7-2, you are going to short circuit it. So essentially, you are going to have like this and then this. Okay, so this is how it's going to look like. Do we get it? If there had been a current source inside, we would have open circuit it. Now, open circuit looks like this. Okay, short circuit is straight. I hope we all get it. Yes. So what you are supposed to do is to find the RTH, that's the equivalent or total resistance. Yes. So what happens in the open circuit here? What happens here is nothing actually happens here. We open the terminals so that we can look through and then calculate the equivalent resistance. So you open circuit it, and then let's say this is where your eyes are. Okay, so Regina, let's say this is your eyes. So looking through this path, the open circuit, what is the equivalent resistance, or what is the total resistance? That is just what it means. Okay, so looking through this open terminals here, we can see that the equivalent resistance is going to be this resistor here and this resistor here, and they are connected in parallel. Now, once again, why are they connected in parallel? They are connected in parallel because they are both connected to the same 2 nodes, this node here and then this node here. Okay, and also I can move from here through this resistor here and back without meeting any other elements. And anytime you have a situation like that, we say those 2 resistors are in parallel. So this is in parallel with this. Do we get it? Now, 1 in parallel with 3, we have product over sum 1 times 3 over 1 plus 3. What are you going to get? 3 over 4. So that is our RTH. Now, what is 3 over 4? Now, what is 3 over 4? 3 over 4, my calculator is giving me 0.75. So this is going to be our answer, 0.75 here. Does the current pass through the open? No, currents, like I said, currents, just like humans, do not like stress. So anytime it sees an open circuit, it avoids it. Okay, so essentially the equivalent resistance is going to be here. Now you ask yourself, between this and this, what is the relationship between them? And the relationship between this and this is that they are connected in parallel, and that's what I just explained. Yeah, I hope you get it. Now, number 6 is asking us to find the currents in the 2 ohm resistor in amperes. So just as I said when I was starting, Thevenin is saying that any any circuit, regardless of how complex it is, it can be reduced into an equivalent simple circuit, which is like this. So now, to be able to find the current that is passing through the 2 ohm resistor, we are going to draw this circuit. Okay, this is our RTH and this is RL. That is the resistor that was taken from the circuit. Now, what is our RTH? RTH, we had, what do we get for RTH? 0.75. What did we get for RL? Hey, sorry, what's our RL? That is the load resistance. It's what? 2 ohms. Now, our VTH, what's our VTH? Our VTH also is 3.25, right? Okay, so voltage, Ohm says that V is equal to IR. Okay, now we want to find a current I that is passing through this 2 ohm resistor. When the current leaves here, it's going to pass through this one and then this one too, because they are connected in series. So it's the same current that is passing through it. So this same I is the same I that will come and pass through this 2 ohm resistor. Now that is the current we are trying to find, the current in the 2 ohm resistor. If V is equal to IR, then I is equal to what? V over R. Now, considering this circuit, our V is our VTH, and then our R, because you have 2 resistors connected in series, we know that anytime resistors are connected in series, their total resistance is the summation of those resistors in series. So here we are going to have the RTH plus RL. So I is equal to VTH. What is VTH? 3.25 over RTH, which is 0.75, plus RL, which is 2. Now, if you punch this, you are going to get 1.18 amps, which is E. So that is the current that is flowing through this 2 ohm resistor here. Alright, so moving on. We are going to consider a question under Norton. So let's hurry. Right. So the question says, it is desired, once again, you've been limited to use Norton's theorem. Not really a limitation, but it is desired to use Norton's theorem to find the currents in the 4 ohm resistor of the circuits below. So the first question is asking us, that's number 7, asking us to find the magnitude of the Norton's currents, IN. The second one is asking us to find the currents in the 4 ohm resistor. Let's call it I. Now, you need to know that IN is not the same as I. IN is the Norton's current, and I here is the current passing through the load resistor once again, the resistor in question. So how do we solve this? Now, the steps 1 and 2 says that we should remove the load resistor from the circuit. Remove the load resistor. And the second step is saying that we should mark the 2 terminals. So after we've removed it, we are going to mark those 2 terminals. Right? And then we are going to put IN. That is the Norton's short circuit current inside. And after you are done, we are going to solve using KVL. Alright, so let's start practically. So this is our circuit here. Let me make it big. This is our circuit. So the first step is saying we should remove the load resistor. Now 4 ohm is our load resistor once again because it is the resistor in question. Okay, we are trying to find the current that is flowing through that one. So the first step says that we should keep everything intact, but this one we should replace it with IN. That is the Norton's current. Okay, so I'm going to keep my 3 ohm resistor intact again, and then the 6V also intact. Alright, so after we are done, we are supposed to solve this using KVL. Once again, you are not limited to using one particular technique to solve for this, but I mean, anytime you are asked to use something to do something, it's mostly because that technique is advisable. Okay, because you can't look at this and try to use, I mean, let me not mention any technique, but it's advisable to always use KVL. Okay, and sometimes to superposition when the sources are multiple sources. I don't know if I have a question inside here like that, but if there is, we are going to do that. Okay, so let's solve this question. Okay, using KVL. Once again, we are going to take loops. Okay, so let's consider this loop here. Now, this 2V here is driving a current, let's call it I1, through this loop. So let's name the loop A, B, C, D, and E. Alright, this 6V here is also driving another current, let's call it I2, through this loop. Let's call it E, F, C, D, and E. Okay, so writing the KVL equation for loop. Writing the KVL equation for loop A, D, C, B, and A. This is what you are going to have. Once again, the voltage source is equal to voltage drop. So 2 is equal to I1 times 1. That is the resistor here. Okay, and you realize that there is no other resistor inside here. So we are going to have just one drop. So 2 is equal to what? I1. Okay, now let's consider the next loop, which is E, F, C, D, E. We are going to have 6 to be equal to what? 3I2, and then you realize that that is the only drop inside here once again. So I2 is going to be what? 6 on 3, which is 2 amperes. Okay, now we have I1 to be 2, I2 to also be 2. Now, don't forget, I1 is coming in this direction. Okay, I2 is also coming in this direction. How do we find IN? Let's consider this loop here. KCL states that, so like I said, you always need to know which particular technique you should use at each particular point in time. Now, looking at this one, we can see KCL can be applied here. Let's consider this loop, this node, the node at C. We can see that I1 is coming towards the node. We can see that I2 is also coming towards the node. IN is leaving the node. What does KCL say? KCL states that the summation of currents entering a node is equal to the summation of currents that are leaving the node. So considering the node, the node at C, we can see that I1 is entering the node plus I2 is also entering the node, but IN is leaving the node. Can you all see that? Yeah, you can't see the question. I'm going to share the question with you, okay, so you see them very well. But let's try and understand. So what's our IN? IN is 2. Sorry, what's I1? Sorry, I1 is 2. I2 is also 2. So what's going to be our Norton's current? IN is going to what? 4. That is the magnitude of the Norton's current, 4. So it's going to be this. Right. I hope it's understandable. Please let's see a yes in it if you are getting it. Can I see yeses in the comment section so I get to know what to do? Please, do we get it? Okay, all right, thank you. So the next thing on board is to find the currents in the 4 ohm resistor. So like I said, IN is not the same as the current that is passing through the 4 ohm resistor. Okay, so the next agenda is to find the currents that is passing through the 4 ohm resistor. Okay, to be able to do that, so Norton also has an equivalent circuit. Norton is also saying that any circuit, regardless of how complex it is, it can be reduced into an equivalent circuit that looks like this. Regardless of how complex it is, it can be reduced into an equivalent circuit that looks like this. So this is the Norton's resistance. This is our load resistance. And this is the Norton's current. Okay, so you are supposed to find the current that is passing through the 4 ohm resistor. This one, that's our load resistor. Okay, now you realize that to be able to find this, we know our IN to be what? 4. And IN is the current being supplied here. Okay, so which technique do you think we can use to find the current that is passing through this 4 here? Obviously, we can use, someone is saying we want a more complex circuit. So this is an MCQ exams, so you don't expect to be seeing those really complex ones. Yes, so you need to know the type of questions you are going to solve for a particular exams you are going to take. Okay, so iron is the current being supplied here. To find the current through this one, obviously the technique we are going to use is current division. Okay, current division. Now we don't know Rn, but Rn is the same as our RTH, that is the total or the equivalent resistance when, once again, all sources have been deactivated. So let's find Rn. In finding Rn, I'm going to deactivate this source here by making it a short circuit. Deactivate this source here by making it a short circuit. And then I'm going to put my Rn here. Okay. So this is how it's going to look like. So always make sure you follow the steps. Oh, sorry. Always make sure you follow the steps so that you don't get missing. So we have our 3 ohm resistor here and then the 1 ohm resistor here. Okay, so once again, as I said, Rn is the same as the equivalent resistance looking through the node here. This is 1 ohm. So looking through here, we have this 1 ohm here and then this 3 ohms here. How do we find the equivalent resistance? We can see that this 3 here and this one here are both connected to these two nodes, A and B. And also I can traverse them without passing through any other elements. There is a node between them, and I can traverse them without passing through any other element. So they are connected in parallel. So my Rn is going to be 3 connected in parallel with the 1. Okay, so product over sum, 3 times 1 over 3 plus 1. What are you going to get? Sorry, 3 over 4. And that's going to be our Rn, 3 over 4. Now, coming back to this, finding the current that is passing through this RL here is going to be I. Let's say I is the current passing through our load resistance. I is going to be, in current division, we consider the other resistor. Okay, so 3 in parallel with 4 over the summation of the two, 4 plus 3 in parallel with, oh sorry, it's 3, sorry, it's 3 over 4. Okay, 3 over 4 times the total current that is being supplied, and in this case that is the IN. And what is IN? 4. Do we get it? So 3 over 4, that is this one, over summation of the two, 3 over 4 plus 4 times the total current coming. Now IN is the current being supplied, so it's the same IN that will come and split between the two. So times the total current, that's IN. Now what's going to be our I? I is going to be 0.63. So B is the answer. Alright, so now let's find, oh, we found the value of the Norton's resistance. What was it? 3 over 4, which is 0.75. That is B. Alright, let's carry on. So our next question is asking us to find the effective resistance between terminals A and B. Now let me deepen this one so that you see it very well. Between terminals A and B of this circuit, we are supposed to find the effective resistance. Now, how do you go about this? Now, given a question like this, the first question you need to ask yourself is, are there any 2 or 3 resistors connected in series or in P? If there are none, then you resort to the use of delta star transformation. Okay, it's very important, a very big disclaimer. Make sure there are indeed no resistors connected in series or in P, that is parallel, because if there are and you try to use delta star, you may get it wrong. So always make sure there are no 2 resistors in series or in P. Alright, so if the transformation is employed, that is the delta star transformation, in situations where there are neither series nor P arrangements, or you can't identify any 2 resistors in series or in P, that is when we employ the use of the delta star. Alright, so if the resistors are connected to each other without a common point, they are said to be connected in delta. If they are connected to each other without a common point, so for example, something like this. You can see they are connected to each other. This resistor here is connected to this, also connected to this, but without a common point. This they are said to be connected in delta. And also an arrangement of three resistors where all the resistors have a common point of connection through one terminal is a star connection. So an example, we can see that this, let's call this RA, RB, RC. We can see that they are all connected here at a common point. So this is star. Do we get it? So let's look at the question that has been given to us. Can we identify a star or a delta? So I can identify a a star connection here. This 6 here is connected to this 6 here, and also this 3 here. They are all connected at this common point here. So this is a star connection. So delta star transformation, is transformation. So we are going to transform the star here to delta. How are we going to do it? We are going to do it by drawing a delta shape around the star. So this is the star. So we are going to draw a delta shape around it. So let's do that. Okay. All right. So let's name this resistor. Let's name this resistor up here resistor RA. Let's call this RB. Let's call this RC. Okay. Now the formula for the star now is star here, and we are trying to convert it into delta. So I'm going to draw a delta around that star. Okay. So the formula for the star to delta transformation is different from the formula for calculating the delta to star transformation. They are different. In this case, there is a star here, and we are trying to transform it into delta. So the formula is the summation of the two resistors that are facing the delta resistor, okay, plus their product over the other resistor. So let's say I'm trying to find RA. RA is equal to summation of the two resistors that are facing RA. So we have 6 plus 6, okay, plus their product, 6 times 6, over the other resistor, this one, which is 3. So we are going to get 12 plus 36 over 3, which is 24 ohms. Do we get it? Let's find RB. Now, RB is equal to, once again, summation of the resistors that are facing us directly. So considering RB, we have 3 and then 6 facing it. So it's going to be 3 plus 6 plus their product, 3 times 6, over the other resistor, which is 6. We are going to get 12 ohms. Now let's calculate RC. RC is also equal to, this is RC here. What are the two resistors facing it? 6 and 3. So we are going to have 6 plus 3 plus their product, 6 times 3, over the other resistor, the third one, which is 6. So we are going to get 12 here. Now, after we are done with this, the next thing to do is, The next thing to do is to redraw the circuit considering the delta transformation, because right now we've converted this from star to delta. So I'm going to draw it again at this side. Okay, so I'm going to draw this one again. Let's look at it carefully. So the 6 is still there, but right now all the resistors that were connected in series are going to be taken out because we've represented them in delta now. So we are going to have our RE 6 is not going to come again. This 6 is not going to come again. This 3 is not going to come again. Now we have RC, we have RB. Don't forget, oh, our 3 ohm is still there because it wasn't part of the star connection. This 3 ohm here is also still there because it wasn't part of the star connection. Now let's join this, and then A and B comes back again. I hope you are following. So this is 6 ohms. So looking at this circuit, we can see that this 6 here, what is RA? We had RA to be 24. We had RB to be what? 12. And then RC was also 12. Okay. Please, if you are following, let's see yeses in the comment section so that I get to know you guys are following. So we can clearly see that this 6 here is connected in P with this 24 here. Okay. Yes. So with the delta star transformation, I could have chosen to use I mean this 3 is this 6 and this 3 here are connected in delta. But if I should use delta, that means I would have to draw the star inside here, a star inside here, and then a star inside. So you realize that I'm going to do plenty calculations, but drawing just one delta makes it very easy. Regina, yes, do you get it? Join one, so you decide on which one you're going to use. If there is a delta and you want to convert all the deltas to star, and after you are done, you find the effective resistance, that's fine. And if there is a star and you want to convert it, so it all depends on the transformation you are seeing in the question. Do you get it? So we can see that this 6 here is in P with 24. Okay, so we can find the P combination of 6 and 24 and represent it by just one resistor here. And also this 12 here is connected in P with this one because they are both connected to the same two nodes. I mean, pardon my drawing, but you can see that we can traverse this path here, without meeting any other element. And also they are both connected to the same two nodes. So once again, 12 is also in P with 3. And also this 3 here is also in a P connection with this 12 here because they are connected to the same two nodes. And also I can move through them without meeting any element. Okay, so I'm going to have 3 connected in parallel with 12. Okay, all right. So what's going to be the P combination of 6 and 12? Product over sum. So 6 times 24 over 6 plus 24. Here 12 times 3 over 12 plus 3. Here 3 times 12 over 3 plus 12. So this is how the equivalent of final circuit is going to look like. This one in P with this one give us this one. Okay, let's say this was R1, this was R2, this was R3. So you're going to have R1 here to be the P combination of 6 and 24. R2 was the P combination of this 12 here and this 3 here. And another one is going to be here. That is the P combination of 3 and 12. Okay, you can join it. Terminal A is here, B is also here. Now, I think from here we can all find the total resistance, because we can see that this one here is in series with this one here. Why? Because it's the same current that passes through them. When the current is coming, let's call it I, and it passes through this one, it's the same current that will come and pass through this. Okay, and also they are connected ends to end. This resistor here is connected directly with this one here. There is no node between them, so they are in series. So you are going to add this and this in series, and the final answer is going to be in parallel with this one. So your your effective or equivalent resistance is going to be, if you should do it well, I think it was, I think it was 5. Yes. So you can punch it and then you let me know in the comment section. I want us to hurry and then tackle the other questions too. So if I convert 1 into star, won't I get a series and parallel connection? It depends. Okay, so you can try it. If after converting 1 to star, you realize that you still can't add them up, that means you would have to consider transforming the other one also into star. You see, after I'd used the delta, everything became straightforward. I had this and this in parallel, straightforward. This and this also in parallel, straightforward. This and this, and it was that easy. Okay, so yes, you can try it. You can convert just one and see. If after doing it, you realize that you still can't make the series and P additions easily, then that means you would have to do it for the other one too, which may be stressful and time consuming. And remember, this is MCQ, so you shouldn't spend more than 3 minutes on a question. Please, can we draw a star within those boxes? Yes, you can do that. Yes, you can do that. But it's going to be plenty. Okay, yeah, you can try that too. Now, moving on. So the person that was waiting for the superposition question, we've gotten to superposition. So this question is saying that, once again, it is desired to use superposition theorem. So if you think you can choose to use any different theorem to do it and get it right, I mean, you can do it. But it is desired to use superposition theorem to solve the question. All right. So what does superposition also say? A minute. So superposition also states that anytime we have multiple sources, you see right now we have 7 here and then we have 5 here. Anytime we have 2 or more sources within a circuit, we can make each one of them act alone and then we solve for the currents or the voltage when each one of them is acting alone. And after we are done, we add them. So a real life scenario, let's say you are sitting in a room, okay, we have people talking. Someone is also somewhere singing. Okay, the fan is fanning, right? And what else? Um, yeah, you let's consider these three. Now, you sitting there, what you are going to hear, the total sound is going to be those two guys talking plus that lady there singing plus the noise the fan is also making. That's going to be a total sound you are going to hear. Okay, so that's what superposition is saying, that you can make each source act alone, and after you are done, you combine the results when each of the sources were acting alone. So this one is saying that we should find the current in the 2 ohm resistor, this one. So we can make this one act alone and find the current that is passing through this one. After we are done, we are going to make this 7 volts also act alone. In that case, this is going to be short circuited. Like I said, anytime we are deactivating a voltage source, we short circuit it. And anytime we are deactivating a current source, we open circuit it. Well, there is no current source here, so yeah, that's it. So in superposition, we make one source act alone. So you see, I drew a straight line here, so I've short circuited it. And after we are done, we find the current, let's call it I1, passing through the 2 ohm resistor. After we are done, okay, we do it again, but this time we short circuit the 7 and then we make the 5 volts act alone. And once again, we are going to find the current, let's call it I2, passing through this 2 ohm resistor here. Now, after we are done, we are going to do I1 plus I2. That is going to be the total current passing through I2 when both of them are acting together. Do you get it? So you make one act alone and find it. You make the other one also act alone and then you find it. After you're done, you add the two. Do you get it? Now, let's read the question very well. It is desired to use superposition to find the current in the 2 ohm resistor of the circuit below. Now, they are saying that we should find the current contribution of the 5V battery. So in this case, there won't be any need for us to calculate it when the 7V is acting alone. They are asking us to find the current contribution of the 5V battery. What that means is that we are going to make the 5V act alone, and then we find the current passing through the 2 ohm resistor, and that is going to be the 5V's contribution. Okay, it's just like saying if the total sound making is those two guys talking plus that lady singing plus fanning, what is the contribution of the fan? The contribution of the fan to the total noise is just when the fan is acting alone. That is when we can know the fan's contribution. So if we want to find the current contribution of the 5V battery, we consider the 5V acting alone. So if 5V is acting alone, what is the current passing through this 2 ohm resistor? Oh yeah, there's a question that requires the use of both. Yeah, I'll see if it's passed, then we solve it because we are running very late now. All right, so once again, this is 1 ohm, this is 5, this is 2. Now, which method do you think we can use to find the current passing through the 2 ohm resistor? Because that's what we want to find when the 5V is acting alone. We can use current division once again. We can use current division because there is a voltage source here, 5V. There is a node here. When the current gets here, it splits. Some passes here, some passes here. Okay. Current division is used when 2 resistors are connected in parallel and they are sharing the same current. Now, this one here is connected in P with this 2 here. Okay, because once again, they are both connected to the same 2 nodes, A, B. And if somebody should traverse this path, the person will go and come back without meeting any other element. So 1 is in P with 2. Okay, all right. So to find the currents passing through this one um using current division, we consider the other resistor, that is 1 over summation of 1 plus the one we want to find, 2, times the total current coming. Now we don't know the total current, but we know the total voltage. So we can find the total resistance, we know the total voltage, and we use I is equal to V on RT to find our total current, and after we come and put it here. Okay, so our V is what? 5. Now let's find the total or the equivalent resistance. This 2 here is connected in parallel with this one here. After you're done, you realize that it's going to be in series with this 3 ohm here. This one in P with this one. You are going to add them and it's going to look like this. 1 connected in parallel with 2, 3 here, and then our 5V comes. So you realize that after you're done, this is going to be in it's going to be in series with 3 here. So let's do that. 1 connected in P with 2 is 1 times 2 over 1 plus 2, which is what? 2 over 3. Now, in series with this 3 here, so plus 3, we are going to have what? 11 over 3. Okay, 11 over 3, that is the total resistance. So I is equal to V over total resistance. So we are going to have I to be equal to 5 over 11 over 3. What are we going to get? 15 over